Hello dear friends, welcome to my channel. Today's discussions is quantum mechanics. Why is probability equal to amplitude squared? Okay, so friends, today I will discuss Born rule. Okay, very soon. So at first, this is the first question is why is probability equal to amplitude squared? Means equals to what? Okay. So we formalized the idea that physical observable are linear operator. Okay. So there is a physical observable is position, energy, and momentum. Okay. In quantum mechanics, we found that the definite states of that observable correspond to the eigenvectors and the definite value that we would measure in that state corresponds to the eigenvalue. In this episode, we are going to a point everything together to intuitively understand the Born rule, which tells us how to determine the probability of a particular outcome. Let's start by formalizing ourselves with some previous results. Let's start by formalizing ourselves with some previous results that the eigenvectors of an observable have to form an orthonormal eigenbasis. So we have a position and momentum eigenbasis which are continuous in normal circumstances, and energy eigenbasis, and so on and so forth. So for our arbitrary quantum state, we can expand our state in terms of a linear combination of those eigenbases, which represent being, okay, which represents being in a superpositions of all those values for the observable. Okay, so if the continuous linear combinations for momentum and position are unfamiliar their refreshing series, note that this is the same quantum state in all of this expansion. Okay, we are just expanding the state in different bases. Let's take a closer look at the energy eigenbasis expansions. This is a closer look. Okay, energy eigenbasis expansion. Given that we have expanded our quantum state in terms of the energy eigenbasis, how would we use this to find probability of measuring an energy, say E4, to begin tackling PE equals to E4. 4. This problem, let's look at the case where we have a two-dimensional vector space. Let's assume that 1 0 and 0 1 are our energy eigenbasis eigenbasis a vector and corresponding to energy values 2 and -2. This is the eigenbasis, and 2 and -2 is energy value. Intuitively, we would hope that a quantum state really close to 1 and 0. Okay, so friends, at first I try to draw a graph. Okay, now because I have chosen 0 and 1 eigenbasis and 2 and -2, I will show it in my graph. So, well, if our state is close to basis vector as shown, the component of our vectors along that direction must be large. Okay, so you can check that at first I -2 and okay. So, so it is the E equals to -2 and E equals to 2, and so it is equals to 2, it is equals to 2. Okay, and this is the component. Okay, okay. So Well, if our state is close to a basis vector as shown, then the component of our vector along that direction must be large. So in this example, the state has a large. So in this example, the state has a large component along the 0, 1 directions. Therefore, our conclusion is that it seems intuitive that the larger the component along a certain eigenvectors, the larger the probability getting that the particular outcomes. Okay, so the larger the component along a certain eigenvectors, very remembering point, friends, you should remember, the larger the component, I just write also, the larger the component along a certain certain eigenvector, the larger the probability of getting that particular outcomes. So let's follow our intuition to start finding the probability of getting an energy of, say, E4. We want to find the component of our quantum state in the direction of the E4. Okay, this is the E4 quantum state. So you may remember that we calculate the component also known as the projection along a certain direction is to take the inner product with the unit vectors. In that direction, note that the order of the inner product matters. We are starting with the and psi and kate projecting ting ting by applying the E4 bra. Okay, E4 bra, this is E4 bra. We just projecting. Okay, and we expand psi and then distribute the inner product. Okay, you will see that we expand psi value. I just expand psi and then distribute the inner product, and since our eigenbases are mutually orthogonal, so we get this value summation I ci e I. Okay, so the only non-zero inner product of E4 with itself. Okay, you know that it is the orthogonal So the only non-zero inner product is E4 with itself, which just gives us 1. So we get C4 inner E4 and that value is 1. So it is only C4. Therefore, the component along E4 is just corresponding coefficient we have hinted. At the idea that the coefficient are related to probability, but now we see why the coefficient intuitively represent how close we are to that eigenstate, and therefore how probably it is to measure it. Okay, therefore how probably it is to measure it. So when an eigenbasis expansion, we want to relate the probability of getting a certain value to the corresponding coefficient of that value. So our first gives might be to take E equals to EI tends to mod of CI. Okay, CI is a complex number. The absolute value of the coefficient this captures the length of the component while taking care of the case when it may be negative. But remember, we could very well have number. Complex number. Okay, complex number coefficients, and when we derive the so danger equation we will see that we need imaginary numbers, so we can generalize this absolute value to be the magnitude of the complex number which still capture the length of the component. Now this is a really good first case, so good in fact that physicist Max Born also initially thought that something like this must be the probability, only later changing it to the correct answer. So why is this wrong? Okay, let's try and get some intuition into why this leads to some problems. For simplicity's sake, let's assume that the coefficients of real numbers and that we are in 2D quantum vector space. Okay, we postulate that the probability of measuring an eigenvalue is equal to the absolute value of its coefficient. Remember that the sum of probabilities over all possible outcomes must be equal 1. So this gives us condition that the sum of the absolute values of the coefficient must be equal to 1. Since we are assuming a 2D vector space, we only have two outcomes. Note that this condition actually implies that the total length of our quantum state is not necessarily equal to 1. For example, let's say both eigenvectors have an expansion coefficient half and our probability condition is satisfied, and but the length of the vector, okay, let's example give one example. This is the, okay, okay, so in here you see half plus half equals to 1, okay, is now 1 over the square. This is not necessarily a problem in of itself. So friends, you see that when it is the norm of, okay, modulus of Kate psi vector space, modulus of the vector space is 1 by root over 2. That value is 0.707. Okay, but this actually introduce another issue. Let's go to the second 2D plane itself and what that is. Okay, okay. Here I have a particular set of energy eigenbasis vector u1 and e2 shown in blue. Okay, shown in the diagram. Okay, e1 and e2 shown, and let's say our quantum state points, okay, shown in blue, and let's say our quantum sense points along 1 0 in the basis. We can expand our state as follows. Note that the absolute coefficient adds to 1, and so our total probability condition is satisfied. Now, looking at a different observable, let's say the angular momentum eigenbasis vectors are L1 and L2 shown in red. Okay, L1 in L2 not shown in blue. Okay, shown in blue when we take our quantum state and expand it in the angular momentum eigenbasis, and we get the following notice: the absolute no longer add up. Okay, so psi 1 by root over 10 e1, okay, minus 2 by root over 10 e2 to 1, and this means that when working in the basis we need to rescale our quantum state in order for the coefficient to still be probabilities. After rescaling the quantum state, we now get coefficient whose absolute values add up to 1. So, depending on which observable eigenbasis expansion we are working with, we have to vary the total length of our quantum state before measuring angular momentum. It may have a different length. Okay. The actual length of our quantum state before we measure anything. Why should it depend on what basis we are working in? And if we assume a particle scale is represented by a single quantum state, then we have an issue. So how do we solve this dilemma? Well, the first thing we should do is question our probability function assumption. So let's instead work with some unknown probability function. So we can write P into E equals to EI. Okay, that is the CI. Otherwise, you can write FCI. We want probability function satisfy two conditions. First, no matter what probability function we choose, when we add together all the probabilities associated with each outcome, it has to equal a constant 1. So this is my condition. Second, we had ideally also want one that ensured the length of the quantum state stays constant in any basis, remembering that the length squared is equal to, write the constant as k squared to enforce that it must be positive. We had ideally also want one that ensured the length of the quantum state stays constant in any basis, remembering that the length squared. Okay, write the constant as k square. K square to enforce that it must be positive. So what probability t function will satisfy? So it may seem hard to find f. So we get, okay, given we use normal equation to solve for numbers. We almost always use differential equation to solve for functions. So our overall strategy is that we should see what these two conditions imply about the derivative of it. Before doing that, let's take a second to analyze the second conditions here to see how all the coefficients relate to each other. Okay. First, what values can we choose for C1? Well, the only real constant we have is that C1 square has to be less than or equal to K square. So C1 square less than equals to K square. There is possibility. Otherwise, the left hand side would be bigger than the right. In other words, the choice of C1 is any numbers between minus K and K. K, okay, it is not this way, it is, yeah, inclusive. If we choose C1 equal minus K or K, then we can see that we had C1 belongs to minus K comma K. Okay, we had need to set all other coefficients to 0. If we wish to satisfy the condition, let's look at the case where we don't choose minus K or K, and there exist don't there exist a constant all other coefficients. So let's instead choose a number a within the range a square plus c square 2 plus c square plus equals to k square. So c1 equals to a. And now what values can we choose for c2? Well, our logic stays the same. We can choose any real number for C2, except now we just need to make sure that C2 square is less than K square minus A square. Okay, so we can write C2 square plus C3 whole square dot dot equals to K square minus A square. In other words, the choice for C2 is any number between these two values, inclusive. Again, let's assume K square minus A square. We stay away from the boundaries of this range and choose a value B for C2 like before. This gives us the following equation, and we can continue the process. So we can continue the process. So C3 square is equal to, if we choose B, C2 is equal to B, so C3 square plus is equal to K square minus A square minus B square. Suppose C2 is equal to B. Okay. So C3 belongs to same method k square minus a square minus b square and root over k square minus a square. Okay. For each C getting a range value for C3, C4 all the way down to Cn, and once we get to here C square n is equal to k square minus a square minus b square minus up to infinity. Okay. What? Okay. Same way. Then well, now we don't really have a choice anymore. Cn can only be plus and or minus the right hand side. So once we have chosen all the, so Cn value is, this is my Cn value. Okay. Okay. Always constant to other coefficient. Cn is always constant to 2 points. On 1 point if the right hand side is 0. So why am I making a big deal out of this? The main take away is that most C are basically independent of each other. As long as we stay away from the boundaries, choosing a C only tell us what range. C1, C2, C3 up to this. So of value the other C can take, but they are independent otherwise. The exception to this is the last C. So whatever we see, we can say they are independent because C1 belongs to minus k comma k, C2 belongs to minus L comma L, and C3 belongs to minus M comma M. Okay. This might seem like a weird overall take away. Cn is equal to plus minus a. Be trust me, this is key to finding f. Last thing, let's establish one more property of f that we will need if we believe that the probability of an outcomes only depends on the size of the projection along an eigenvector, then the associated probability should not change if the projection of is pointing along the eigenvector or against it, as long as they are the same size. Mathematically, a backwards pointing projections manifests as a negative coefficient. So in other words, our intuition tells us that f should not care if the coefficient is positive or negative. Okay. So f is an even function. So f is even function. Hopefully you see why this makes a lot of sense. With that, let finally do some mathematically heavy lifting to find f. Let's start with the first condition and let's single out the term with the last coefficient, and now we can use the second condition to solve for Cn. Okay. and then we can plug this into the second term here. Okay, now here we use the fact that f is even function to get rid of the plus minus. So now let's follow through with our original idea and set what we can learn about the derivatives of f. Since c1 is a independent variable within its within its range, we can take a derivative on both sides with respect to c1. And since the right hand side is a constant, we get. So for any Ci that is not C1 inside the sum, varying C1 does not really change that Ci. They are independent, so all the terms in the sum are equal to 0 except the term with C1. In the term we pulled out, we simply use the chain rule to take the derivative with respect to C1, where we again use the fact that the C1 don't direct depend on each other. This is a subtly argument, so take some time to really understand what we did. Rearranged this equation to get loose C1 terms all on the left, and we get the following. Now there is nothing special about C1. We could have done the exact same thing, except now we take a derivative with respect to C2, and all the same argument would apply. Since C2 is just as much as independent variable as C1, we had get the same relation except 1 by C2 dfc2 divided by dc2 is equal to f dash. Okay, C2 dfc2 divided by is the formula. So except with C2. So all the sum argument would apply since C2 is just as much as an independent variable as C1. We yet get the same relation except with C2 on the left. But note these two equations have identically right hand sides. So we have that these two quantities must be equal to each other. So we can write. So to see what this implies, that like let's take a derivative with respect to C1 on both sides. So let's now think think about what the right hand side derivative is asking. It says that we should vary C1 and see how much the value in the parentheses corresponding changes. Well, as long as C2 is within the allowable range, it does not change. It's all. It's free to be what it wants, even if C1 changes by a bit. In other words, the derivatives must equal to 0. Since C2 does not directly change when C1 changes. This is another really subtly argument, and it's the key to finding f. So we can write. Okay, so take a second to make sure really understand why we were able to say that the right hand side must be 0. Used superpositions of variable technique. Once we do this, we can take a step back and look at what we have. This is our differential equation for f. So we can now integrate both sides, and more time we get the following, where we remember to add a constant. Constant integrations mu. So fc is equal to, is not this exciting. We finally see that the probability function must depend on the squares of the coefficient. All that's left is to find the constants of integration. To do this, let's first think about what f of 0 should be. In other words, what should be f0? So the probability be in this case that the corresponding eigenstate has zero coefficient. This case our quantum state has zero component along the eigenstates, so it should be intuitive to expect that the corresponding probability is zero. So we have f of 0 is 0. So mu is equal to, we can say mu is equal to 0. Okay. To figure out the other constant, the integrations, let us do the condition 1 against, let's fc1, fc2 plus fcn equals to 1. Assume that c1 takes the maximum value k, and therefore all the other coefficient have to be 0. So fk is equal to 0. Sorry, fk must be 1. Sorry, fk equals to fk equal 1. Okay, so as fk plus f0 plus up to equals to 1. So f0 is equal to 0. So fk is equal to 1. Now plugging in this condition, we will tell that lambda must be 2 divided by k square. So plugging this equation fc divided by, so lambda k square by 2 is equal to 1. Okay, lambda equals to 2 divided by k square. There we have our final result given the coefficient of an eigenstate expansion. The probability associated with the eigenstate must be equal to the coefficient squared divided by k square. So probability associated, so E equals to, which remember is just the length of our quantum state. Now note that we have some freedom with k. Our only condition was that we wanted our quantum state to have a constant length in any basis, but we have the freedom to choose what that length is. As conventional, it's simplest to choose that our states should have magnitude 1. Hence k equals to 1. So lastly, if we have complex coefficient, then it makes sense to generalize this is the complex magnitude squared, and so we have the following magnificent result. If we take all quantum state to have length 1, then the measurement probability associated with a particular eigenstate is equal to the amplitude squared if a squared of its coefficient when we expand our state in the eigenbasis. Also remember that we found that we can find the coefficient using the following inner product. This rule for probabilities is known as the Born rule. Born rule. The foundation of Born rule is known Gleason theorem. Is only valid for vector space of dimension 3 or greater than 3. At least two independent coefficient, at least two independent coefficient at least 3. Okay, so friends, I will discuss more about the Gleason's theorem. Okay, so this video is very helpful because we can learn a lot of topics like the probability. Please check my total work. Okay, so thanks for watching.